Okay, so next up we want to find the inverse function for f of x equals x times the square root of 4 minus x squared. And since I have no idea if this has an inverse, and I really don't want to verify it algebraically, we are going to graph this thing. So we've got x times the square root of 4 minus x squared, and we're going to look at that and say, guess what? It doesn't pass the horizontal line test. It does not have an inverse. Boy, that was an easy problem, right? Because you know what this problem asks for? Does an inverse exist? No. Find the formula for the inverse? Not applicable because it doesn't have one. And this one, now could we restrict the domain? Yes, but finding exactly where that should happen is a little iffy, and this question doesn't ask for that anyway. But we could find the extremum. Looks like point A is at a kind of an ugly point, so we're not going there. All right. So some properties of functions and their inverses, and this is just kind of things to know. We've already talked about if the point xy is on the graph of f of x, then y comma x is on the graph of f inverse, and that is because what the inverse function is, right? So I always like to put examples here, right? Like if it's the point 3, 4 on the function f of x, then we know 4, 3 is on the inverse. And as we kind of just saw in the previous example, the domain of f of x becomes the range of f inverse, of course with y's instead of x's. And that happens exactly because of the definition, because we swapped x's and y's. And conversely, the range of f of x is the domain of f inverse. And of course the graph of f and f inverse are reflections across the line y equals x. That 45-degree line, we've seen that in several problems so far. Okay. So, and like I said, one way to think about an inverse is that it undoes whatever operations the original function did. So kind of following that logic, if we compose f of x with f inverse of x, we should get back the original input. So this brings us to one more property for inverse functions, that f composed with f inverse is equal to x. And for this one, unlike what we saw in the earlier chapters, order of composition doesn't matter because they are inverses. We are going to get out the input x for all x that are in the domain. Okay, so we want to use composition so we can kind of use that fact to show that if we've got two functions, to verify that they are in fact inverses of each other. So for this one, we've got f of x equals x plus 5 all over 4, and f inverse equals 4x minus 5. So if we, let's see here, go back, f of f inverse, we want to do that one first. So that would be, I'm going to draw this as everywhere we've got an x in f of x, we're going to put in f inverse. So we're going to put in 4x minus 5. So when we simplify this, we're going to end up with 4x minus 5 plus 5 over 4 is equal to x. And then if we do the same thing in the opposite order, we're going to have 4 times whatever, 4x minus 5. What's going in the box? It's the input, f of x. And when we simplify this, the 4's are going to cancel. I'm going to get x plus 5 minus 5, which is, of course, x. And if you want, we can graph the functions. It's never a bad idea. So we'll go pull GeoGebra up, turn off the previous stuff, and we're going to put in x plus 5 over 4, and we're going to put in 4x minus 5, and we're going to go turn on our 45-degree line, and we can see, yeah, these do look like they're reflections of each other. But again, you want to make sure that your scale on your graph is 1-to-1. So if you go to settings, it's a good idea to make sure that this 1-to-1 x-axis, y-axis, that little lock icon is locked. Because otherwise, if it's not, let's see if I can do it. You might get something like this. Now we're not 1-to-1. These don't look like they're reflections of each other anymore, right? So if I go back to settings, I'm like, no, I want this to be 1-to-1, and we are going to lock that. And it's, as soon as there we go. Now we're back to it looking like they're actually reflections. Okay, so we're at the 5-minute mark, so let's pause here, go to the next video.